All right. Well, thank you, Manish, and welcome everybody. It's so great to see everybody. And yesterday was just so fantastic to see the hundreds of ski alumni coming back over the years. So I get to introduce our amazing speakers today, and our first speaker is Pat Hanrahan. I met Pat more than 30 years ago when he came to Utah to visit some of our amazing graphics alumni, Robert McDermott and Michael Cohen. And Robert told Pat, "Hey, you should come meet this new kid that we hired named Chris Johnson." And so I've known Pat and enjoyed our relationship over those many years. Pat has multiple Utah connections, as you will find out. He's a world-renowned researcher in computer graphics and visualization, and he really typifies the interdisciplinary research and education that SCI so values. He started his academic career as a nuclear engineer, right? You have a bachelor's degree in nuclear engineering at the University of Wisconsin, and then did a PhD in biophysics. And along the way, he taught himself computing and computer science and graphics and visualization as a way to do the data analysis and visualize results from the experiments that he was doing. During that time, he met one of our famous alumni, Ed Catmull, who was at the New York Institute of Technology, and Pat was recruited there by Ed and worked with Ed and planted the seeds of RenderMan, which is the software that has made so many wonderful Pixar animated movies in the past. Pat has a list of a long list of awards. I'll just mention three, actually four. The 2003 Stephen Coons Award in Computer Graphics, which is the highest award given in computer graphics. The 2006 IEEE Visualization Career Award, again, the highest award in visualization. He has 3 Academy Awards. And in 2019, he shared the ACM Turing Award with Utah alumni Ed Catmull. And we are so happy and honored to have Pat Hanrahan join us today. So Pat, please.
Thanks, Chris, for that nice introduction. It's so great to be here for this celebration. I'm sort of always in awe of Utah. I mean, obviously the history in computer graphics. I've worked with Ed Catmull, I've worked with Jim Clark, I've worked with John Warnock, I've worked with so many alumni here, and they were really the leaders in the field. I'm actually another generation after them, so I'm a little younger than them, not that much. But then, SCI is equally remarkable to me. I mean, most of the second half of my career, I was really interested in high performance computing and visualization. And Chris and everybody at SCI sort of, to me, were the leaders in that area. So, every chance I get, I like to come to Utah and talk to all the people here and then be inspired by what's going on. So I think SCI is sort of a unique place. And I'm going to give you sort of a little bit of a personal history. This talk is a bit historical, but I think since this is a 30th anniversary celebration, it could be important. But the title of my talk starts out as a menagerie of high performance graphic systems. And I actually chose the word menagerie. I don't know, I hope everybody knows what a menagerie is. If you look it up, it's like a collection of wild animals that are kept for study, it's like, or another definition is a diverse collection of ideas, things, and people, okay? And I think that's sort of what this place is. I mean, it has this character. So I'm going to give you sort of, and I think it's really important to have menageries, okay? And I'll explain that. But I'm going to give you sort of my menagerie, okay? It's not the same as your menagerie, but it's related. It's very similar. So that's what I'm going to talk about. So I'm going to start with sort of, a sudden event happens, So to me, one of the big events was this paper in 2012. I'm sure everybody knows about it. It was by Alex, Ilya, and Jeff Hinton. And what they did, and the abstract is actually quite clear, you can read it, but there was this ImageNet database that Fei-Fei Li had created, which was 1 million images which were labeled, okay? And there was a lot of people were interested in image recognition. So that people were trying to write programs that take those images and say what's in the image. classify the image. And then Hinton was always a big fan of neural networks. In fact, he sort of kept neural networks alive through the dark ages of neural networks. And he believed in deep convolutional neural networks. So what they said is, we're going to build this really big neural network. It had 60 million parameters, which is by our standards today is very tiny. Had 5 layers, and then actually I'll just mention it had a top layer. So these were convolutional neural networks, and then the top layer was this all neural network that sort of did the final reasoning. And then so they had a lot of data, and they had a big model with a lot of parameters. And then they said, well, if we could train this thing, we could probably do really well in this competition. So they got 2 GPUs. And that's what Alex did. So they each had a different role in this paper. And Alex was an undergrad. Okay, doesn't get the credit he deserves, like a lot of undergrads. He actually got it to work. He got it implemented on GPU. Ilya and Hinton didn't know anything about GPUs, so he did all that. And they entered the competition, and they beat everybody by almost a factor of 2. So they had an error rate of like, what was it, 15%, and the next best player, best entry was 26%. So it was like just blew them out of the water. And so this led to this idea that suddenly if you combined a lot of computing power with a lot of data, with a deep convolutional neural network, that you could solve really hard AI problems. And so that's a huge thing. And if you see, this is a graph from a recent paper. There's lots of graphs like this, but there's this place where like people are getting certain progress with image recognition and so on. It's doubling every 24 months. Suddenly it changed to a completely different curve. So there's the pre-GPU era and the post-GPU era, okay? And the curve is such that you're now doubling like every 3 months to 2 months, okay? So it's just completely changes. And then since that paper comes out in 2012, you see that if you look at this logarithmic axis, there's actually a 1,000,000-fold speed up in the training of models and the scale of the models. And so that's quite remarkable, right? I mean, they just changed the course of AI with this. And now you just see the fastest supercomputers in the world are these NVIDIA, systems. And I know there's a lot of NVIDIA alumni here. Congratulations for all the great stuff you're doing. Actually, I just got this when I was here yesterday on Twitter. This picture was posted of Jensen delivering to Sam Altman and Greg Brockman the next H200 system, the very first H200 system. So this suddenly appears, and everybody that sees this sort of says like, wow, it's amazing, just revolution, what happened? And I guess I'm trying to tell you, like, what happens is there's a long buildup to this kind of thing where people invent all these ideas, and then suddenly it breaks through and it becomes a big thing, okay? And I hope you can sort of get where I'm going with this, okay? So let me tell you sort of my story of that long journey a little bit. And I'm gonna, one thing that surprises people a lot is like, why are the GPUs the fastest computers in the world? Like, I used to go to all these scientific computing conferences. They didn't pay any attention to imaging computers or GPUs. They were working on crays and connection machines and stuff like that. Well, the reason GPUs became so fast is people in graphics and imaging and scientific computing were fanatical about getting access to more computing. Okay, and I'll just show you how fanatical I was, okay? What crazy things I did. Okay, here's me as a grad student. So a little younger, a lot younger. I was a biophysics student in a wet lab, okay? You can see the faucets in the background, okay? Just doing experiments. And I was working on modeling the nervous system of a nematode, Ascaris lumbricoides. And so in the process, I was trying to figure out how to do this. And I went and I looked up this guy in the computer science department, Leonard Ure, and he was like the time the world's expert on neural networks. This is in the 80s, because most of the neural networks had died out completely by then. They sort of boomed in the 50s and the 60s, okay? And then they sort of got stamped out, right? If you know the history of them. So, but he was one of the last remaining guys that was studying them, and he wrote neural network software. And he got, around the time I was there, he got really interested in computer architectures for neural networks. So this is an example of a book. He wrote many books, multi-computer architectures for artificial intelligence. And if you look at this is a convolutional neural network on the cover. I mean, this is, if you look at it, you can sort of see the repeated patterns. And then you also see these like weird like projections of hypercubes and stuff. He actually had a convolutional neural network with this like more general network above it. So the convolutional neural network did all the imaging, and then this more general network would do the reasoning, sort of the last stage. Very similar to that Hinton architecture, right, where they had the all-to-all connection at the end, and they had the convolutional neural network. And anyways, and he was writing this stuff, and it was incredibly slow. Like he'd have like 100 neurons in his neural network and so on. So it didn't work very well. So he was desperately seeking cycles. And so he hired me to implement neural nets on a fast computer they had just acquired. What was this fast computer? Well, the computer science department had got a VAX 11780, which was unbelievably slow. And we in this imaging group had got this crazy computer called the Stanford Technology Corporation 70F. And this was actually designed a few years earlier. This was about a $250,000 computer. It was in the space science department, so I would go over to the space science department, and it was designed to process satellite imagery, both from Landsat satellites, weather satellites, reconnaissance satellites. And it had this crazy architecture. You see these big squares on the left? Those are like the frame buffers. So there's a red frame buffer, a green and a blue, but they could have more than three. And those were 512 by 512 by 8 bits. Okay, this thing cost $250,000 at the time. Okay, then what these things did is they fed their data into these, this little box, next box you see is there's 3 lookup tables, what are called input function tables. Then there's an ALU, which is an adder usually, and then an output function table. So with this you could do a multiply by, taking the log with the table, adding the numbers together, taking the exponential, and then what you could do is either bring it out to the display, or you could feed it back, and it could get combined with what's in one of these frame buffers. And this thing it ran at 30 hertz because that was video resolution. And so you could do about 7.5 million multiply and accumulates per second, actually 3 times that, maybe, so maybe 20 million multiply and accumulates per second, which was like way, way faster than the VAX. And so my job was to get this thing to work. That was it's probably the first paper I ever wrote in my life, 1982, okay? And, parallel array processing on pipeline display terminal, okay? And here's an example of a program I wrote back then. This is a language I designed, so I was really interested in programming languages and parallel computing. This is the game of life in my language. It's almost like low-level assembly language because every one of these statements is sort of like one pass of the pipeline display terminal. And actually, Len had this really clever thing, which I really love. I wish that this had caught on. If you take 2 vertical bars, that stood for a parallel statement. That ran in parallel, okay? Isn't that nice? I was, just out of high school, learned geometry. Made total sense to me. Okay, anyway, but this was my program. And so I built this whole system. And then I implemented neural nets, and we made the neural nets probably like 1,000 times faster at the time, but they still weren't anything like that. So, I just sort of trace this because I'm really fascinated with neural nets now and computing, and I'm just saying this was like an early idea. This was not like a new idea. It's just the computers are a lot faster now. We were very inspired by this thing called the MPP. And this was a system built by NASA. This is actually a picture I took. If you go to the Space Museum near the airport in Dulles, they actually have this on display. It's worth checking out if you ever see it. This was built by a company called MassPower. And actually, I think one of the main architects at NVIDIA is John Nichols, who did a lot of the general purpose GPU hardware design architecture, as I understand it. I talked to him. He actually founded this company. So these ideas about parallel computing and using them for imaging and building massively parallel things were around from the earliest days. Now, I subsequently went to Pixar, and the reason I got the job at Pixar, I wanted the job in animation. I wanted to work with John Lasseter, I wanted the fun job, right? I got the job being the software product manager for the Pixar image computer, which was also a pretty fun job. But it was a lot more fun hanging out with John Lasseter and making movies than it is writing microcode for the Pixar image computer. But that's what I knew. You know what I mean? I knew about parallel programming languages. I knew about the algorithms. I knew about image processing. So that's what I did. And I'm not going to spend much time on this. I'm going to go through a couple other machines here just to sort of give you a flavor of how crazy these early machines were. But this just sort of shows this. It was a four-way processor, and you had a scratch pad memory and a big frame buffer. But I'll just sort of mention, like, this thing had a bunch of features that we now take for granted, and many of these were not new features in the Pixar image computer. They were also done in earlier computers, like this four-way SIMD. Like the four-way SIMD we had was very similar to what we do now in a lot of SIMD instruction sets. We had what's called tessellated memory, where you could fetch a row, a column, or indexed. We had a predicated control flow. This is a pretty big thing. If you do a structured program with if then else, there was the SIMD processor knew about structured programming, and so it handled all the bit masking automatically for you. And it did very efficiently skip instructions if the predicates were all zero. Again, a very common technique in SIMD computers. And we did we invented our own number representations. We had this 12-bit number representation where the numbers went from minus 0.5 to 1.5 because we were often computing on pixel values, and we wanted a little room for overflow up and above. But we mostly were bounded between 0 and 1. So anyway, just all these sort of ideas just sort of keep evolving over time. So anyways, I spent a lot of time doing that. Actually, I wanted to show you. Did my computer just froze? Oh, yeah. Just for fun. I don't know. Can you read this? I don't know. I grabbed some of my old code. I really like to write microcode. So just to show you what that's like, okay? Because how many people have written microcode? Probably not a heck. All right, yay. A few, not many. Okay.
Screen sharing got disabled.
Oh, okay.
Re-enable this.
Yeah. Let's do my whole screen this time. Can you see my screen? Yeah. Okay. Anyways, just take a look at that. I'm not going to explain it. I mean, maybe I actually wrote documentation for what it did. I don't know what it does anymore. Anyways, but it's crazy, right? But we wrote we didn't even have a C compiler for this thing. We wrote everything in microcode, okay? And we built a complete, library of image processing routines writing code like this. In fact, I remember this one because this is what's called image compositing, where you do A over B. And I remember when I got a hold of it, it took 11 cycles or 11 ticks per pixel. And when I got done with it, I got down to 6. And I can still picture in my mind, the screen getting refreshed at this rate versus that rate. You know what I mean? I mean, just the difference, was very tangible. So anyway, I actually really enjoyed that. So anyways, but that's what it was like. So I would say that's somewhat fanatical. Okay, now, why did I do that? Well, I was really interested in visualization. So even though I didn't get the good job doing animation, but I got an even better job doing visualization. So that's when I wrote the volume rendering paper. And that's probably how I got connected to Chris and everybody here, because I was working on Chuck, obviously, as volume render, other people here. And so, but this was from my first paper on it, where we were analyzing CT scans. And what we basically had shown was this computer that, which was really built for image processing, could also be used for graphics. Now, that may seem like a simple idea, but there's this great similarity between graphics and imaging and things like that. And it was just really a fun time, because I just would, if you read my paper, I have about 20 pictures in the paper I would just get all these data sets from everybody, like this was there was this guy at the Monterey Bay Aquarium that scanned in the sea otter, and he sent us the data, Anyways, it was a lot of fun. So, and we'd just get these random data sets, volumetric data sets that people would have, and we'd be able to make pictures of. So it was really quite stunning. And that really got me going, on visualization. And that's really why I was so willing to program these machines and work on this low-level stuff, because I could do all this cool stuff. I mean, I could just do cool stuff. And, Pixar, eventually I started working on rendering again at Pixar. And this idea that if you could have a lot more computing power, you could do cool stuff was the whole premise of the place in some sense. If you talk to Ed Catmull, he said he had you wait for 20 years, for Moore's law to catch up to what they thought they needed to make a movie. So you had this long time to think about things, a long time, and you need to have some people that were willing to fund you during that time. You know what I mean? Because 20 years is a long time. Most people, their time horizon is not 20 years. And their funding horizon is not 20 years. But Pixar actually had a 20-year. Ed has written about this. I'm sure maybe he's come and talked about it here. It took 20 years for people. But this was just what they thought was the minimum to make a movie. You know what I mean? If you let their imagination go, they would think, oh, we need even more computing power. So we built a lot of different computers there. This was one I built as well. A lot of people don't know that I did all this kind of stuff, but we built this computer out of transputers, which was a computer back then made by NMOS, 16 transputers. We actually designed something we called the raise machine. And what I was doing was I was implementing RenderMan, but most of I was writing the specification, but most of my time was spent like designing this hardware with some other people and learning and writing a programming environment for it, and then implementing the algorithm. So it was a co-design effort with hardware, compilers, and software libraries, and application. And it was three big things, and there were three of us working at it. So that only took three people. And then of course what happened, that really, we weren't really that good at building hardware. And people like SGI and get Jim Clark now, another Utah alumni. I just show this picture because this thing, this graphics architecture stuff just sort of started to evolving. And I think a good way of thinking about what happened in this period in the 90s is this diagram, because it sort of shows sort of what SGI sort of ended up with as their architecture. And again, you sort of see there's two big parts to it, right? You have a big imaging part, which is the biggest part, the lower part, which is processing all the pixels, because there's a lot of pixels. And then there's this upper level part, which is called the geometry board, that processed triangles, and there were fewer of those. So there's often, different stages to these machines. But what was nice about SGI, and I think they just had a really big impact on the world, is because and Kurt, he designed some of these machines, not all of them, but the reality engine he did, for example. And he set down this architecture for graphics, and it sort of caught on, and that led to modern things. And NVIDIA, I'm a huge fan of NVIDIA, obviously. But they claim there was essentially this milestone. I'm leaving out lots of stuff. I could go on for hours and hours going through all these various stages and so on. But eventually they got to a point in 1999 where you could put the entire graphics pipeline on a single chip, hence a GPU. And it's doesn't take, this had 17 million transistors. I mean, if you think of the billions on a chip now, it's not that many, but that is a milestone when you get it on a chip, and that's why they coined the term GPU. And then, everybody here knows about that. I mean, there's lots more to say about this, but the earliest graphics machines led to these massively parallel machines. And I remember at the time collaborating with a bunch of architects. I did a big project with Bill Dally, Mark Horowitz, John Hennessy, and others, Kunli Ulukatan, people at Stanford and others. And there were various camps at the time. There were camps. There was like the SIMD camp, where everything did the same instruction. Then you had the multi-core camp. So Bill was just sort of in the SIMD camp, and Kunli was in the multi-core camp. He built one of the first chip multiprocessors. Then there were other people at Stanford that building these all multi-threaded machines. And each of these were this like a way of getting a certain amount of parallelism. What was quite remarkable about GPUs, and I will sort of say it's because there's this insatiable appetite, is we needed as much parallelism as we could get, and you needed all of these to build a cost-effective machine that scaled up to that size. And so they were, people, again, back to this fanaticism, they were willing to sort of try to figure out how to put all these things together. NVIDIA people can tell you more about it, but they figured out how to put these all together and scale these machines up to be incredibly parallel. And this is a time when most people weren't very interested in parallel computing, to be honest. I mean, if you talk to various big vendors, they might they'd be arguing about whether you should put 2 cores on a machine or something like that. Suddenly you have machines with many, many, many cores. And it seemed like very natural in graphics and visualization and imaging to require this kind of machine. So this quest, for cycles, like you just have these problems that need more cycles, and you just want to keep doing it. I remember reading, I was listening to a podcast from Ilya, who was on the original AlexNet paper, and he said, we know these neural nets can use an arbitrary number of cycles. The only other applications I know that really do use them at scale are graphics and imaging. Because they just, I mean, and he's saying to the point where people will buy large machines and there's a large market for them. So this quest for cycles continues. So this curve is going to keep going, and there's going to be a lot of innovation there. So anyway, that's just a sort of a story about that. Just to summarize it, I mean, I think sort of my lessons from that are twofold. One is, you always want to pick really demanding problems that require you to innovate. Image interpretation and modeling and intelligence, that's actually what I started out with. I was in neuroscience and biophysics. That was a really demanding problem. We needed a lot of cycles for that. Games and movies obviously are similar to that. We needed way more cycles than were available. And having this problem, having a problem-driven approach was critical. We weren't just architects. We weren't just compiler people. We were people trying to solve a problem, which is a different mindset, and we did whatever we thought necessary. The second thing is you sort of have to home in on certain fundamental technologies, and lots of times the technologies that win go out of vogue for long periods. So neural nets, I mean, I thought neural nets were the greatest thing in the world when I was in grad school, but they were so out of vogue, I talked myself out of working on them. Literally, I talked myself out of working on them because my advisor was having a hell of a time surviving doing that. Nobody else thought it was worthwhile. And so but and by the way, when I was in grad school, all the major ideas had already been discovered. Convolutional neural networks had already been discovered. Recurrent neural networks had already been discovered. Stochastic gradient descent had already been discovered. Backpropagation had already been discovered. I mean, people had all the algorithmic. I mean, they've refined them, but the basic ideas were all there, and yet still, it wasn't enough. Not everything was there to make it work. And so, but they were a really good idea, and I still thought they were a good idea. And then parallel computer architectures and languages, similar kind of thing. The people studied them for a long time, but now they're having their heyday with this distributed computing and so on. And so, it takes a long time for these things to sort of have their day in the sun, and you need places, which I'll call these menageries, where you can develop and encourage diverse ideas and innovative people, okay? And you just want to keep them alive, you know what I mean? Like Hinton kept neural networks alive. I think that's why he's my hero. He just kept them alive when nobody else cared about them. And then, it's like biodiversity. Like, why do you want diversity? Well, you want these things around so when the world changes, okay, then you can quickly adapt to the new situation. You have new problems, new technologies, more data, bigger computers, and now suddenly they become the right way of doing things. And so their time will come, and so these really bad ideas from the past become the really good ideas now, and they just suddenly appear, but they've been all figured out, you know what I mean? I mean, people figured out a lot of this parallel computing stuff in the 60s and 50s and 70s. And so, once the time came, once we could scale them up. And so you need places. I was actually at Pixar, which I thought was a bit of a place like that, where Ed Catmull had this 20-year vision and we could develop technologies, algorithms, hardware, movie making skills. And I think Ski has done that a lot, both at Utah and for the country, is to just bring together all these different people, keep all these great ideas alive. And so that's one reason I admire the place so much. And so happy 30th birthday, Ski, party on. Thank you.